So I think this presentation is, related to what Dr. Savelli just presented, but I'm gonna talk about like in general terms, not in just in medicine. So it's called AI agents, opportunities and risks. Okay, this video. So what is an agent? According to the International Organization for Standardization, an agent is an entity that senses inputs, for example, like sounds or images, using sensors and responds through effectors to its environment. AI agents possess autonomy, so they can operate independently, and also possess authority, so they have permissions to perform actions to achieve specific goals, and in this way modifying their environments. So the core components are the user input, which can be text, voice commands, whatever. We had an environment, the operational bounds for the agent. It could be physical, like an autonomous vehicle, or it can be digital, like a business or an intranet. So it has sensors, which are the mechanisms for perceiving the environment. It can be cameras, microphones, or it can even be things like digital queries to databases. It has a control center, which is the core processing unit of the agent that helps making decisions. It has percepts, that is the data inputs received from sensors. It has effectors, which are the tools used to take actions, which could be physical devices or digital commands, and it can perform actions. So a very brief history. So AI, has evolved from rule-based systems in the 1950s down to sophisticated agents, right, capable of learning and adapting. So early AI rely on fixed rules, making them predictable, which that's good, but unable to learn from new experiences. The introduction of machine learning in the 1990s marked a major shift, allowing AI to learn from data and improve over time. And since 2017, with the introduction of the Transformer, uh, um, large language models have further enhanced AI abilities in natural language processing and understanding, enable human-like text generation and complex interactions. So today, AI's agents use techniques such as reinforcement learning, transfer learning, which I'm gonna talk a little bit here. So over the past like 25 years, advances in computing capacity, data availability, and algorithm innovations have significantly enhanced AI capabilities. So large language models and large multimodal models have transformed natural language processing and the generation of various media, including text, images, audio, video. And a range of techniques have greatly improved AI through increased efficiency and greater specialization. Examples are things like, of course, supervised learning, reinforcement learning from human feedback, and transfer learning, which involves taking a pre-trained model, typically trained on a large data set, and adapting to a new but related problem. So these and other paradigms often used in combination have dramatically expanded the problem-solving capabilities of AI agents in various areas of application. So We can talk about deterministic AI agents. These were rule-based. They operate with fixed rules and logic. The decision making is transparent and consistent, which makes the outcomes predictable. That is good for certain areas, such as medicine. For example, we want to know how it came to that conclusion. However, these systems cannot learn from new data or adjust to changes. They just follow predefined paths. Now we have the non-deterministic AI agents. These are data-driven. This includes like, from machine learning, deep learning to large language models. So they make decisions based on the statistical patterns in the data. They look like they have intelligence, but some experiments have shown that it's just patterns that learn from the data. Since they learn from data, they can adapt to new situations by interpolating its knowledge that was learned during training. However, the problem of this is that they are hard to interpret. Of course, they are commonly referred as black boxes. And then we have the current state, right? Where we have multi-agent systems. We're going to talk a little bit in a future slide. So type of agents. So we have the simplex reflex agents. So these operate on a perception of their environment without consideration of past experiences. So they follow predefined rules to map specific inputs to specific actions. The implementation of condition action rules allows for rapid responses to the environmental stimuli. Examples include things like basic spam filters that use keyword matching, like simple chatbots. Before ChatGPT, there were simple chatbots with predefined responses, and automated email responders that sends pre-written replies following specific triggers. We also have model-based reflex agent. These are designed to track parts of their environment that are not immediately visible to them. So they do this by using store information from previous observations, allowing them to make decisions based on both current inputs and past experiences. Examples of this can be like a smart thermostat that optimizes energy usage by adjusting to current and historical temperature data, as well as user preferences. Things like a smart robotic vacuum cleaners that use sensors to map and navigate efficiently the environment to avoid obstacles and optimize cleaning paths. We can have things like irrigation systems that use sensors to collect real-time data from environmental factors such as soil, moisture, temperature, and precipitation in order to optimize water dispensation. Then we have goal-based agents. These are able to take future scenarios into account. This type of agents consider the desirability of actions, outcomes, and plans to achieve specific goals. The integration of goal-oriented planning algorithms allow the agent to make decisions based on future outcomes. And these make them suitable for complex decision-making tasks. Examples of these agents include like advanced chess engines that have the goal of winning the game, planning moves that maximize the probability of success, things like route optimization systems for logistics that sets goals for efficient delivery, things like plan optimal routes, by setting clear priorities, and customer service chatbots that set goals to resolve customer issues and plan conversational flows to achieve their goals efficiently. Then we have utility-based agents. These employ search and planning algorithms to tackle intricate tasks that lack like a straightforward outcome, thereby going beyond a simple goal achievement. They use utility functions to assign weighted scores to potential states, enable optimal decision making. These are grounded in decision theory, and allowing the agents to effectively balance like multiple possible conflicting objectives. Examples of this include things like autonomous driving systems that optimize safety, efficiency, and comfort, like portfolio management systems, such as like robot advisors that can make financial decisions, and healthcare diagnosis assistants that analyze patient medical records, label patient data, and optimize treatment strategy recommendations in cooperation with doctors. Okay, so advanced AI agents and systems. So this is the architecture. It's a little bit different to what I showed before. Now we have like a list learning part here where the agent can, learn over time from past experiences. Then we have this control center, which directs the user input to the model, which normally is like an LLM, like a GPT model or like a cloud model or whatever. And we have other components, like we have memory to store past experiences, and also like to keep track of the interaction. And we have tools, right, to allow the agents to access to data, access to the internet, and perform actions. So we have the concept of an agent system, which is an organized structure that integrates multiple heterogeneous or homogeneous AI agents. Each agent is typically specialized, possessing its own capabilities, knowledge, and decision-making processes. They can share data collaboratively to achieve the goal of the system. There are different possible designs for this, like central orchestration, like this one, where multiple agents cooperate, and we have this orchestrator that combines and manages the agents. Or we can have like a mixture of agents where each agent is called sequentially, and the agents processing the outputs of the previous one. So let me give you an example. For example, an autonomous vehicle. This is an AI agent system that includes agents for perception, for path planning, for localization, for infotainment. And each of these are specialized to specific tasks, right? And they work together in a coordinated and centralized manner to ensure that the vehicle reaches its destination safely and efficiently, right? Prioritizing the passenger comfort and safety. So the future of agent is what is called the mass or multi-agent systems. So it's basically a network. It can have like a network architecture like this one, where they all communicate to each other. Or it can have, like I mentioned before, like what's called a supervised architecture, where you have a nation that coordinates with the others. This is already happening in different industries. So let me give you another example. For example, in a smart city, we can have like a multi-agent system that manage traffic flow in real time using vehicle to everything communication, that enables vehicles to interact with other vehicles, vehicles that can interact with pedestrians and road infrastructure. So each traffic signal is controlled by an AI agent system that communicates with nearby signals. For example, if an accident occurs, AI agents can reroute traffic, can adjust signal timings, can notify emergency services, and can communicate with other vehicles and pedestrians to avoid the area, right? All with minimal human intervention. This is a possible scenario that we will see probably in a short time. Okay, what are the benefits? I mean, there are a lot of benefits in different areas like software development. Companies like OpenAI and Meta, they are saying that this year they will have AI software developers already working for them. In healthcare, like just Dr. Sabelli presented, Dr. Watson, in customer experience, education, and finance, there's a lot of opportunities of these agents to make impact. Of course, with great powers, there comes a great responsibility, as Uncle Ben said to Peter Parker, right? So there's a lot of risks that we need to take into account. And if you are developing agents or the agents developers needs to try to minimize, right? For example, AI systems can independently pursue misaligned objectives, right? So that agents developers need to put guardrails for this. AI agents can learn to deceive human operators, for example. And so on, right? There's a lot of risks that can happen. So it can have technical risks like problems with the agent itself physically and in the data that it was trained. There can be socioeconomical risks. Increasing the autonomy of AI agents could reduce the human oversight and increase their reliance to carry out complex tasks, even in high stakes situations. There can be societal resistance that society want to use them. Employment implications, as I mentioned, it's expected that by this year there will be agents working in the industry and financial implications, right? Organizations could face like higher costs associations with the development of these agents, such as expenses for securing software system against cyber attacks, managing associated operational risks, and also, I mean, if they run locally, they need a lot of power, right? A lot of computation. There are ethical risks, as always. We have like ethical dilemmas, transparency challenges that I mentioned. These state-of-the-art agents or models are like black boxes that we don't know exactly what is happening inside. So we need to address these risks and challenges to understand specific applications and environments. In high stakes environments like healthcare or autonomous driving, where human lives are involved, even minor errors can have serious consequences. While in low stakes scenarios, such as customer service, the risks are significantly lower, right? So it's needed a systematic risk analysis to identify and assess these risks, allowing the stakeholders to implement effective mitigation strategies. In conclusion, the development of AI agents has evolved from simple reflex systems to advanced multi-agent systems capable of planning, learning, and making informed decisions. Recent advances in LLMs and LMMs have enhanced their autonomy, learning capabilities, and collaborative functions. While AI agents can reduce the need for human oversight and streamline tedious tasks, this decreased oversight might increase the likelihood of accidents and vulnerabilities, right? So to address safety, security, and societal impacts, we need further research, focusing on both technical solutions and governance frameworks. So it is crucial for stakeholders across different sectors to collaborate on developing consensus around governance mechanisms for these technologies. Thank you very much.